Okay, today we started consideration of energy conservation, and in using the Reynolds transport theorem to describe energy conservation, we needed to first be clear about what defines the energy of the fluid. And so we're going to define capital E to be our quantity B, which is 1/2 mv squared, which is the usual kinetic energy, plus mgz, which is the usual potential energy, plus E sub T, representing the thermal energy. Now with this definition, we can say, that should be capital E sub T, being the thermal energy. With this definition, beta is going to be defined as little e, and we just divide each term by m, and we get 1/2 v squared plus gz plus little e sub T, the thermal energy. Now the time rate of change of the energy for a system is equal to the exchanges, the rate of exchanges of energy through heating and through work. And we're going to divide the work into two components. So we have the rate of heat added to the fluid, and then this is the work done by the fluid. The division of this into two parts represents external forces, and then this is going to be the pressure forces. Work against those pressure forces. This is the rate of work, rate of heat that the fluid is exchanging with the surroundings. Okay, now there's a fair bit of manipulation that goes into this next step, but I'm going to write it down as the sort of the general form of conservation of energy equation. So you have the heat that's added to the fluid. We have work done by the fluid against external forces. This would be pumps and turbines and these types of external exchanges of energy. And the right-hand side then is going to just be d by dt, the energy in the control volume, where that energy, to remind you, is the quantity shown at the top here. And then we have our flux terms, and those fluxes are the integration over the control surface of rho. And now I'm going to write out formally little beta, because we have 1/2 v squared plus gz plus p over rho plus the thermal energy. And then the flux of fluid, of course, is, as we've had it in each of our conservation laws, v dot dA. So what we have is the little energy, the energy per mass, represents these three terms. We have this fourth term that appears in the flux, which actually arises from this work term. But it happens to have the same mathematical form as these flux terms. And what you see starting to emerge here is the Bernoulli group, v squared over 2g and so on. And in fact, that's the next step in this derivation, is to assume steady flow. Assume QH dot equals, or goes into the right-hand side, with the thermal energies, and they become a head loss term, H sub L. And then we let WS dot, and we're going to divide by rho GQ, the flow rate, is going to be written as the head added, or head extracted by turbines minus head added by pumps. And by dividing everything by rho GQ, what we get is quantities that everywhere are proportional to length, or have units of length. And so in this format, then, we can take those flux terms and consider it going from, say, from phase 1 to phase 2 for a closed conduit. And we end up with V1 squared over 2G plus Z1 plus P1 over gamma plus any energy added by the pump is equal to V2 squared over 2G plus Z2 P2 over gamma plus energy extracted by the turbine plus head losses. And this is the generalization of Bernoulli, accounting for energy added by pumps, extracted by turbines, and lost to friction. In the case of inviscid flow, those head loss terms go away. Let me add one other factor here, alpha 1 and alpha 2, and that accounts for the integration of the energy over the cross-section. In turbulent flow or along a streamline, alphas are 1.